So today we are going to cover three things. First, how you plot things with Matplotlib. And then the second part will be on object-oriented programming. This is not a course on object-oriented programming, so it's more an orientation of what object-oriented programming is, because Python is an object-oriented language, and you have already used the methods in the strings, for example, for using the objects. So we'll go through that. I will also do a more graphical example of how you can, what the benefits of object orientation is. And then finally, I will go through CALFEM, CALFEM for Python, the version that we have in this course, that will also be used probably in other courses in the future. So we are moving from MATLAB to Python. So starting with Matplotlib. So this is a Python module. So it's similar to what you have with NumPy. You load it as a module. If you have used MATLAB and the plot functions in MATLAB, you will probably feel quite familiar with how it's used here as well. So the commands are very similar. However, there is an underlying graphics library in Matplotlib as well that you can use that gives you even more functionality than you have in MATLAB. So how you use it. So the first statement here, Matplotlib inline here. This is only for use when you're using Jupyter notebooks or notebooks. So if you're using standalone applications that we are going to primarily do in this course, you use the second line here. So you do import matplotlib.pyplot as PLT. So this is the convention you use in the same way that you import numpy.mp. You use this. So every command that you plot command will have the prefix PLT. And you can also see here that the matplot module is divided in several submodules. And pyplot is a simplified module for plotting. So it contains all the commands that you have in MATLAB. And the Matplotlib library, this one here, is the larger library that has much more features. But we are only going to use the pyplot in this course. So, simple plots is done with the plot command. And you can see here that most of the commands can take any input. So it doesn't have to be NumPy arrays. It can be lists. It can be anything that you can iterate over and contains numbers. So it's hard to plot ASCII characters. So let's see here. Why is this stopped now? Oh. Okay, I don't know why it's. So here I have 4 numbers in a list, and then I do plot.plot and then show. If you are using notebooks, you don't have to do the show. It will plot automatically. But if you have a standalone application, a script in code, you need to do the show. That is what brings up the window on the screen. So if plotting NumPy arrays, it's probably here where you will use it the most. So in this case here, what you do is you create the X range that you want to plot. And that you can do with the linspace command in NumPy. And that will generate a series of values between a starting value and end value. And then you can specify how many values you want. And then you can do y equals mp.sin x. As I said, NumPy can process, calculate on an entire array. So when you call the np.sin function, it will actually compute sign for every value in x and return that to y. So if you run this, you can see here that you get first the range x here, and then the y here is the y values. And then we can do it just like we do in MATLAB. We can do plot.plot, and then you give x and y series. And it will look like this. Then just like MATLAB, you have more options that you can specify on the plot command. So x and y, those are the series, and then you can specify a third parameter here, which is the line type and color. So in this case, R stands for red, and O is rings. So it will draw all the series with red rings, like this. And then you can have, the first is color, and then the marker is an O in this case, and then a dash. That means you get dashed lines. So, or you have a line between them, and then each point is marked with a circle here. You can have double dash, then you will get a dashed line like this. And you can have plus, that is a plus marker instead. And you can have a plus marker with lines between them, like this. So it's a very powerful plotting toolkit. Yeah, skip that one. You can also have multiple series in a plot, which is very common if you want to compare something. You can have multiple series. What we can then do is we create a single series X, and then we create Y1 and Y2. So in this case, we have two functions, sinus and cosinus, and I want to plot them in the same plot. Then you can add series in groups of 3. So in this case here, I have one series here that is consisting of the X series, the Y values, and then how it should appear. And then the same thing, you have X for the next line, and then Y2, and then its parameters. And then you get two plots like this. Then you can have, there are many properties you can set on the plots. There are many options of specifying these plots as well. So one way is that you add named parameters in the plot function here. So in this case here, I add the line width parameter. That will set the line width for both of the series to 4. So they will be 4 pixels wide, like this. But if you just want to have specify on a single series, then we need to get the plot objects out of the plot function. So in this case here, we can do line 1 and line 2. So when you plot, plot will actually return the series objects that you can, for each of the series that you have. So line 1 and line 2, these are Matplotlib objects that you can set parameters individually. So in this case here, we extract line 1, line 2, and then line 1 dot set line width. And then we set a wider line width on line 2, and then we plot here. So then you can see you can change the sizes of the different series. And if you have three series, you will have to add a third parameter here in the plot section. You can also, instead of assigning specific objects for each line, you can actually get a list of line 2D objects, and then you can use the set p command of the plot library to set properties for all the objects in a certain in a list. So in this case here, we get our line objects, and then we set the line width to 8 for both of them. And then now both of them are 8 in width. So you can also plot multiple figure windows. So if you're running it standalone, like we are doing in our program later, you can create a new window by doing plot.figure. And that creates a window, and then the plot will go to that window. Then you do figure again with a different number, and then the plot will go to that window. And you can also do specify figure 1 again, and then you can plot additional things to figure 1. So the figure command will create a window if there is no window, or set the window to be active if there already is a figure 1. And when you run this in a notebook, it will look a bit strange. So you will see two kind of plots on top of each other. But running it standalone will produce 2 plot windows. You can also divide up, in a single window, you can divide up the view in multiple subplots. And this is a bit of a strange syntax here. So what you do first is that you create a figure, then you create a subplot, and the two first variables are subplot 2 rows and 1 column. So this is the specification of how the subplot should be laid out. The third parameter here is the current subplot we are going to plot to. So 2, 1, 1, you have to specify 2, 1 for both of the plots, and then 1 and 2 for the actual subplot to be plotted to. So this will look like this. So this is a single plot, and we have 2 rows and 1 column. Then you can do 1, 2 instead, and you have 1 row and 2 columns, and then the first plot. Then you have it this way around. You can decorate plots. So it's almost a science. Yeah, sorry. Yeah. Alltså du vill ha separata fönster?
Ja, precis. Jag vill göra först en salto.
Ja.
Sen vill jag till salto. Nu vill jag samma salto. Döpa.
Ja, du kan bara ha... Alltså, om man säger det här kommandot här, om vi går upp tillbaka här igen. It's the same thing as doing a figure, but inside the window. So you say, okay, I want to plot in the first subplot of 1, 2 plot. And then you call another subplot, and then you switch the focus to that one. And then all commands will go to that subplot further on. You can try, if you load this, you can experiment yourself with the commands. I don't like this syntax here, so I said that. But I think it's modeled on Matlab again, so that's why. Then you have so the creating plots for scientific papers or reports is kind of almost a science, and you have to specify a lot of things in the diagram to make it readable and understandable, and there is a lot of extra commands in the plot routine here to do that exactly. So in here you have the subplot we discussed before, X label and Y label. Here you can give textual labels to each of the axes. And it looks like this. So here you can see that I have a Y label and a Y2 label here and X here down below. And those are added by the X label and Y label commands. And as these are subplots, you can see here that you don't have a label here on the top plot. It's the same axis here, so it puts X on the bottom. You can also add text to the plot. And here's one of the cool features with the Matplotlib library. You can actually give it math equations directly in. So it can interpret math equations with something called the LaTeX syntax. So there is a special how you specify math equations, and you can use them directly as a string into the text command here. So here you have the position here. This is the position in the plot coordinate system. So it's not pixel based. You can place the text in the right coordinates of the plot. Then you specify the text, and then if you want it to be aligned horizontally, that is the point will be in the middle of the text. And you can set left, right, top, bottom, and so on. So if I run this here, you can see here that it added an equation here. Sin x equals to pi divided by 2 here. So equation here, and it's placed here in this position. You can also do arrows, so you can basically have an arrow that points to a certain point, interesting position of the plot. Then you can give a text here. Then you have x position that it should point to, and the text location. And then there are some properties here for the arrows. And when you run this, you can see here that you can point to the max position of the plot. You can also limit the plot size, so where you want to plot. By default, it uses determines that by the bounds of the series going into the plot, but you can use the X-lim and Y-lim to limit the view of the plot. So in this case, I want to show only from 0 to pi and from 0 to 1. And you can see here now that I've zoomed in on the arrow here. You can also change the scaling from linear to logarithmic using the X-scale and Y-scale commands. So you have plot the exponential function. If I comment this out here, you get this here. And you can do that in both directions. Now I will go in. The Matplotlib is super documented. And I will show where you can find all this information here. So if you go into the Matplotlib library here, okay, you go to examples, you get a page here with all the diagrams that you can produce with Matplotlib. So just you have an idea, you want to plot something, you go into this page here with all the diagrams, and then you click on a certain diagram, and then you get the code. So then you can take this code and modify it yourself. So you don't have to kind of look in documentation too much, just look at what kind of diagrams do you find here. And then, okay, I need to do some kind of isolines, and go in here and look how the code has to be done. So it's very, very well documented. So I will just go through some examples here of plots that you can do. So you can do histograms. That is, you have bins that you put count in, and then you plot the number of values in each of these bins. Looks like this. You can do normal bar charts. Looks like this. You can do scatter plot. That is, you plot points, the x-y coordinates, which also can have a color value. You can do contour plots. These are a bit more complicated. In this case here, you have to create X series and a Y series, and then you create something called a mesh grid. And then that mesh grid you can use to create expressions. So if I run this here, you can see that X here is actual X values in a grid, an array. And then you can create C values here by using NP sin and then creating expression. And then you plot that either using contour F for filled, and it looks something like this, or you can do contour, and that will create contour lines instead. You can do images, and in this case here you have to download an image first, so I will do that. So there is a module in Python here. You will notice here that in Python there is a lot of built-in stuff. So before you start implementing your own functions in Python, look at the runtime library. Is there something I can use? And there, for most things there are. So in this case, url-lib request, that is a module that can access the web and download stuff. So in this case, I use request. So I want to go out to the web and get an image. And in this case, I go into some place here, and then I download an image called 6502 JPEG. And then now this is a file on disk. So to be able to display that in Matplotlib, you need to read that file in, and you can do that using plot.imread. That will read this file and store it in an image. look, it can plot the image. So then you just do imShow, and then you give it the image, and you can see how many pixels there are in this image. You can also control how the image should be displayed. So if you have very few pixels in the image, you can tell Matplotlib to smoothen out the image so that the image looks smooth instead. And there are multiple interpolations method that you can choose here in the plotting. So if we run this one here, you can see here that this is the original image, and then you can see how it can interpolate these using different methods. You can do streamline plots. So if you have a vector field, you can plot those as well. Bar chart, yeah, you can do this kind of chart as well. This is the variant of the bar plot, which is which has sectors with a additional dimension. You can do three-dimensional plots as well using the plot surface. You use the same method as with the two-dimensional contour plots, but now you use instead plot surface here. Then you get a three-dimensional plot as well. So this was a very short introduction to Matplotlib. The reason I will not cover it in more detail because the documentation is so good. And you will also, in the CALFEM library later on, you will see that there are a lot of methods that will use Matplotlib to do diagrams. So CALFEM will have used Matplotlib as the implementation layer. So that was Matplotlib. So let's switch to object-oriented programming. Can I get this to move? So last week we already did some object-oriented programming. We used objects. So when we create strings in Python, the string variable is actually an object. And the object can have a lot of methods that you can call on it. For example, split is a method that is a part of the string object that gives you a split version of the string. So objects are usually described as nouns. It could be a point, a circle, a model, a square. An array is also a noun. And you interact with objects by sending them messages. And the messages are the verbs that you want to perform something on the object. You want to transpose the matrix. You have a.t, and t is the method that transposes the matrix. And you send a message to the object by calling its methods. Those are the verbs. And then you have, every object also has attributes. So a point, for example, has attributes x and y for the position in the room, or even z. So data and methods are connected together into an object. So in normal programming, function-based oriented programming, you have a function, you pass the data to it, you get data back. Object-oriented programming, you create an object, you interact with the object, so you don't pass the objects, you can't pass it to the function, but the object itself knows how to, for example, a position or point knows how to move itself, a circle knows how to also move and also change the radius, for example. And objects in Python are described by classes. And classes is a blueprint for an object. So you basically do a blueprint on how you want your object to look like, and then you can create multiple versions of these objects. So you can create multiple points that all work the same way. They share the methods, but they have unique data. So just to kind of illustrate the differences between object-oriented programming and function-based programming. We start with a function-based example. So here I have several Python-based functions. I have a function here called createPoint. It returns a list of x and y. So we have a very simple data structure. We have a list that represents a point. If we want to move the point, we need to pass the point list over to the function here. So you can see here, point here is the data, and delta x and delta y is what we want to move this point. Then we modify the point here, and we don't have to do more than that because we modify it in place, so we don't have to return it back. We have a method called 0 point that will set the position to 0. We have a set point that will assign the values to the point, and we have print point. So let's define those. So this is how you use it. So first you have to create a point, and we have a function that will create a point, return p. And note, we don't really have to know about what the data type of p is, just that it is an information bearer. So it contains the information, this is my point. Then we run this, so it prints out the point. So we have a method that just prints out the position of the point. Then we move the point, we pass the p variable over to the move point function. And you can see here that the point position was updated. We set it to another coordinate and we print it, and you can see here that it sets to -2 and -1. And it's still there. So this is how you do it in function-oriented programming. You create a data structure that holds the data. It has no relationship to the functions. So the functions and data are separate. And all functions need to take the first argument is the data that you want to manipulate. So you pass the data along, and the functions modify the data. So this is function or procedural programming. So let's go into classes then, how we define classes in Python. So classes are the blueprint for objects in Python, and a class describes what attributes the object should have, which methods it should have, and you create an object from this blueprint. In this case, there's a special notation to do this. So for example, if I have a class planet and I want to create the Mars planet, I give it a variable named Mars, and then equals to planet with uppercase. So this is the class construction. This creates a planet object, and Mars is now a planet, an object based on the class planet. But you can create Jupiter as well, and then you have Jupiter is also an object of the class planet. They each have their own data structures, so their own attributes. I will come to that here. For example, it can have a position X, Y, Z in our solar system, and Mars has different coordinates. But they have basically they are the same class of planets. A class is defined similar to a function, but with instead of using the def keyword, we use the class keyword. Class point will defer. So here I declare my class point. Then there is a special method called init, and init is the constructor is called. This method is called every time the user creates an object from a class. Init is called, and that is so that you, as a designer of the class, can initialize the variables, create the attributes, initialize them to reasonable values when the object is created. And also, there is a special parameter called self, and this is something it's often very hard to grasp in the beginning, but the class is a blueprint. The actual object is somewhere else. So when you create an object, Python will allocate memory for that in memory, and that is where the data for object is stored. But when you design the class, you need a way of referencing this data in a way that it is not specific to that memory location. And self is a parameter that is the actual location of the data in memory. So that's why you have to specify self here. And self here, you assign X and Y attributes to the actual object that has been created. So let's do that. So what you now can do, we can try this out. So I added another one here that you can illustrate how when the constructor is called. So when I run this here, you can see here that when I create an object of the class point with ID, you can see it prints out the memory location of the ID, and you can see every time I call it, this ID changes. So every time I create a point, you will get a new object. So P ID is not the same as Q ID. They are the same class, but the object itself is different. It's like you create multiple strings. Every time you create a new string variable, those are different. The same thing here. So the init method will also make sure that the attributes are created and initialized reasonably. So you can see here now I can print out p.x, so I can access the attribute of the object by using the dot notation. And you can see here that q and p both are 0. But you can of course change p and x and y, and you can see here that both P and Q are different objects, and they have their own data connected to them. So in object orientation, there is the notion of encapsulation. That is, you shouldn't directly access the attribute variables inside a class. You should have methods to access them so you don't go directly. So for example, X and Y here could be stored in a database somewhere, and you want to be able to access them. The user of your object shouldn't have to know how the internal workings of the objects looks like. So I will come through that this is not a big problem in Python. I will show you later, but first I will show how it's done correctly in other languages as well. So in Python, it's very difficult to hide things, because there is in many other languages you can set that the variable should be private and not accessible outside. But in Python, everything is public basically. But you can hide things by putting 2 underscores in front of the attribute here. So here I create a point, and you can see I do self underscore underscore x equals x. So the incoming parameters are assigned to internal variables here with a special prefix x. When I run this and I run this here, you can create the point normally, but then I try to access the attributes internally here. You get an attribute error because we have hidden the internal storage. Those are hidden inside. We can't access them. You can't even access the internal type here. It's also hidden. So how do we access the internal attributes? Then you add methods to your object. So if I want to access the x value, I have an x method that returns the value, and I have also setter here that sets the value here. So in this case, I don't have a return here, but I call x and I give it the value. And you can also see here when we call this object that self, you don't have to think about self when you're using an object. Self is only used when you declare a class. So if I define this one here, you can see here that you don't give self to the when you call the method set or x and y. That is handled automatically. So basically this p here is actually the self. And Python will give that into the, when it calls the set method on the class here, it will actually pass the p over to that method automatically. It's just that because we can't know in beforehand what the self is going to be, we need to have this variable to when we declare the classes. So now you can see we can set the variables, but we still don't have any way of getting them out. So we also add simple functions that just return the internal variable. So x here returns self x, y returns self y. And now we have the ability to get the values inside. But wouldn't it be nice if we can use the just p.x and have the same functionality with encapsulation. And you can do that in Python as well. So there is something called properties. And properties is a way of controlling access that looks like you are assigning an attribute directly, p.x equal to something, but it calls methods to do that internally. So here I have a modified version of point where I have getX, setX, getY. So I have explicitly created functions that have get and set. And then at the end here, you can see here that I have x equals a property, y equals a property, and then you can see here that I have a getX and setY. So property simulates an attribute by when you assign p.x, for example, it will call setX. If you use the variable, it will call getX. So I also added some print statement here to show how it looks. So here, now we can use the object just like we did in the first example. We can do p.x equals to 42, p.y 84, even if we have internal hidden variables. So you can see here that first what happens is that p.x equals 42, that calls setX. p.y, set y. And then we print px, you can see it calls getX, prints that out. Print p.y, get y. So this way you can control access and let the user of your objects have a really easy method of accessing your attributes. And you can still have control. You can do really easy read-only attributes, for example, that you only allow it to be get. You don't allow the set method. That means that the user can only get things out. It can't reassign the objects. But there is another way that is even more easy to use. You don't have to give the property declarations here at the end. You can use something called decorators instead. And decorators is a high-level feature of a language. Basically, you tell Python, I want a property of this function. So in this case here, you do @property. Then this function will be a property. And then you have to have, so that will give you the read that you can get x out of the object. If you want to set it, you have to do @xSetter. And then you give a function here that has self and a value as second parameter. This one only requires you to have an x that returns a value. So in this way, you can very quickly create a property-enabled class. And it works the same. So here I have the setter for x, property of x, property of y. So in object-oriented programming, the idea is that you interact with the object using the methods. And we can add some additional methods here. So for example, I want to move this point. Then I can implement the move method. And in this case here, I just specify dx, dy. And then internally here, I just modify the x variables here with the delta x here. And then you can call move here. So I create 2 points, and I move them. And then you should be able to see that I have to define it as well. So you can see here that after the moves that the coordinates has changed. Another method that could be good is to have a method that can copy copy the values from a different object into your own objects. And this is copy from, and you have a point here that goes in, and then you assign self x p.x, self y p.y. And that's the same problem we had before. If you do p2 equals to p1, they just reference the same object. So if you want to have really a copy from another object, it's a good idea to give the copy from. This is just how it looks. No, I didn't. And then there are some really interesting things as well. There are something called special instance methods. And you have already seen one of them, and that is the init method. That is called when you construct an object or create an object. But there are other things that you can use. For example, there is the str method. So just to test it out, so if we print an object, so if you print an array, for example, you get a nicely formatted array. But if we print our point class here, you get this strange thing here. And that is because the point itself doesn't know how to print itself. And there is a special method that you can implement that is called when you call print on an object. So in this case here, we go into add this str method here below. So that is called when you print an object. So instead, there is a default string in the base object of Python, and that will return you this kind of strange output that we saw here. And in this case here, it will print out point, x and y coordinates like this. So let's run this. And now when we run this one here, you can see we print out something that is more comprehensible. And that comes into also classes as data type. So when you have defined your own class, that is a data type in Python. Just like a float, integer, it has the same kind of value. So you can use it just like any data type in Python as well. So here I have a list of points, and I can do a loop over here to add some points to this list. And then we run this like this. And then I will show you a shortcut for doing this in a single line as well. This construction here you can do in a single line like this. It's just that you have an implicit loop inside. So you have point random for I in range. And that will create a list without the loop construct here. It's a bit faster, but not much. What you can do then, you can loop over the points and just print them out. Works like this. And you can also see that when you have created variables like this and do P2, P3, you can see here that it works like normal Python variables. So if you do P2 equals P0, P2 points to the same objects as P0. So they work just like any data type in Python. Let's see here. Okay. And another feature object orientation is class inheritance. So suppose you have a point and you want to create a new object that has almost the same functionality as the point. So a circle. The circle adds a circle with a certain size, and we need to kind of add the radius attribute to the point to the circle. So what you do then is you create a circle definition here. You have to have an init here, and you have x and y just like the point, but then you add the radius parameter here. And before we start adding our attributes to our circle, we need to initialize the inherited object first. So because the point at the x and y coordinates, they are not defined yet. And what we do then, we call a special method called super that will return the inherited object. And then we call its init here. And then we pass along the x and y coordinates here to the point class to initialize x and y. And then we initialize our internal r. And then we add setter and the properties here, copy from, and we have a new print here as well. And we can use this class. We can create a point and a circle. And you can see here that all the methods that we defined in our point, they can be used on the circle as well. So we can reuse the code here. I need to define the class first. Like this. So you can see here, print will call the correct method on the correct class here. So in this case, it will create a point and a circle. And when you print the C, it knows that it should call the str method or the circle method. So let's break 50 minutes. Just to finish up the object-oriented part here, we looked at inherited classes. There is also another type of class called composite classes. And composite classes are classes that combines multiple objects into one. Typical one would be a car with wheels. So the car is a composite class consisting of wheels and engines and stuff like that. You compose them together. There is no inheritance relationship between the objects. So just an example here could be a line. It doesn't inherit from object or from the point, but it owns 2 points. So the starting point and the end point here. And then we have a property here that returns the first point and returns the second point. And then we add a string method here. So what you can do then, you can use it like this, line, create an object, and then you can assign P0x, P0y coordinates like this. Yeah, this one shouldn't be commented out. Wait a minute. So it has a line from point 0.0,2 to 3,4. The thing is, if you look here, we only have properties. We don't have any setters. That means you can access the points, but you can't reassign them to different point objects. So in this case here, if I do this here, you get an error here because it has no setter. So let's fix that. We add setters here that just reassigns them. And then we define this object. And then you can use it like this. So you can create new points here and assign them to the points of the line. And then the natural method of a line would be a property that returns the length of the line. So here we add a length property that does this calculation here and returns the length of the line like this. The choice of having only read-only properties is something that you have to decide yourself. If you want to keep the ownership of the points yourself, you don't want the user of your object to reassign the points, you don't give it a setter. You only give it a property. So that is a design choice. There is no, you need to yourself know what you want to accomplish with your objects, and decide after that if you want to be able to reassign them. Polymorphism is a really interesting concept as well, and that is when the programming language will call the correct method depending on the object type. We have already seen some of these in action, the underscore string method. So for example here, I have created a shapes list and I just add a bunch of things to this list. And then I do just loop over and call print. And by polymorphism here is that when I call print, Python knows which str method to call. And that is that it can look at what's coming in here. Okay, this has a string object, they call that one. If an object doesn't have class doesn't have its own str, it will call the top level str. So there is always an str method. In Python, every object inherits from a base class called object. And that class has a base set of methods that it implements. So you will never have a class that doesn't have a string method. So if I run this here, so you can see here that I can, it works. It will, point will print out as a point, circle will print out as a circle, line like this. But what is 42 and 42.0? These are floating point integers, and it still works. And the reason is that the floating point value is actually an object itself. So this actually works. 42.0 point str. So even the floating point number is an object that you have that has methods that you can call. And that is why this loop here works, because it can print out the floating point. It has its own method of printing itself out. And what you can also do, you can have, for example, move here. It's called, you move all circles here in a single go. And it will, so in this case, circle doesn't have its own move method. So the first thing that Python does is look at the object. Does it have a move itself? No, but its top level object has a move. And then it calls that instead. So it goes up the object hierarchy and finds where the method is implemented and calls that. That is polymorphism on a high level. So what I'm now going to do is actually go from my notebook here to Visual Studio Code. And I'm going to do a graphics example. And this example uses something called Py5, which is a creative coding library for Python. So it's very focused on drawing graphics. So what I want to do here is implement a very simple particle system. So basically a lot of objects moving around in the box. And what I've done here, first here, I defined a class that will be the base class for all my drawable things. So I call it drawable base. And you can see here that I don't create properties if I don't need to. These are simple attributes. They don't have to be protected by property getters and setters. So I just assign them as attributes here. So I have something for the line color, the fill color, the width of the lines. I have a method here called onDraw that I will I override that with the implementation classes later on. And to draw this object, I call draw, and that will call some methods of this library here to set up the colors and stuff like that, and then it will call onDraw. So in this case here, I want to implement a particle, a round particle, and a box boundary class. And then I want to create a particle system here. So in this case here, this is the setup of the entire program. There is a settings method here that is called to set up the window size, 600 by 600. Setup function is called once. The thing I do here is that I tell the library all ellipses should have its base point in the middle. So this is just a convention here. And then I call draw here. So now the code is empty. There is no implementation. And you can see also that one of the most powerful functions in Python called pause. And the reason for we have a pause function in Python is because you can't create a function without a content. You need to have statements in a function, otherwise it doesn't work. But if you want to have empty function, you need to put a pause. So it does nothing, but it is a valid statement that does nothing. Very powerful. So if I run this now, it should bring up a window like this. So we have an empty sketch here that I want to fill with my particles. So the first thing we're going to do is we are going to implement our particle class. So I have my cheat sheet here. So what we need to do first, we have to remove the pause here. And we need to create an init function. You can see here it always does this for me. And I think we can use that. So what we do first, we define our init method. We need to have parameters in that defines the position of the particle. We have x and y coordinates, and we have velocities. So initially we say that the velocity of the particle is 0, so it doesn't move. We say that it should have a stroke width of 2, so it's visible on the screen. We need to add a method for updating the position of the particle. So we do a def update, and we give it also a delta time here. And then we just add x to it. So in this case, we do x equals to self vx multiplied by the time step. And now we need to implement our def on draw self. And we could just do a simple here. This is the simplest form here. We have a point, and it's x and y. So now we have something that has all the attributes. You can set the stroke color, the fill color, the stroke width. All those attributes is also contained in the particle here. So now we try to set it up. We create the particle here and set up. Self.p equals to particle 300. we skip the, and then we draw the particle here just. If we run this, let's see if we can see anything with this one here. No. Can you see the small particle? Yeah, it's a single point here. What we can do now as well, we can update here we created a particle, we can draw, but we need to also, if we wanted to be able to move, we have to set self.p.vx here, and we can do, I'm not sure what this. We set it in one direction here. We set it to 30. So we just move it in one direction, and we set this to 0 and 0, like this. And then we do, before we draw the particle, we do self.p update. And here we do, because the sketch here is updated every 60th of a second, so we give it the delta t to 1 divided by 60. Now you can see that we have a moving particle. But this is not a very fun particle. We need to do something more that we can see. So what if we do a round particle? So we implement here, and you can see here I already inherited from particle. So we need to, now we have the moving part, we have the update part, it's already part of the particle. So now we only have to update basically the drawing function and the radius of the round particle. So let's create an init here, def. Let's see what the AI is. Yes, that's good. So we can also have a stroke with it too, so we have a bit wider fill color as well. Yeah. Now we can keep them at 0. So we see we add a R parameter here, and we add our R2 our attribute here. We init the particle here with X and Y. That will call the init of the particle. Now we have to implement the def on draw, and then we do sketch. It's really smart, this program. I don't have to do my cheat sheet at all. So now we have a round particle. So let's change that. We create, instead of a particle, we create a round particle like this. And we give it a radius of 40, like this. But we don't have to change anything more now. We can have the same parameter, the Vx and Vy. And when we do run here again, you can see now we have a big sphere. We give it a bit different stroke color. So now we want to create more particles. Before we do, you need to kind of check that the particle stays inside the box. So in this case, I will cheat a little. I have this already defined, a box boundary here. So this is a class that sets up the boundary of the bouncing stuff here. So I'll just copy that over to my, paste it in like this. So what is that? It sets up the box that it will check. So x min is 0, x max is 600. There is a method here called if the particles is inside the box. There is also a check here that what happens if it bounces on the sides, it reverses the velocity and stuff like that. So next what we have to do is to we need to create more particles and a boundary condition. So we start by doing self.particles equals to an empty list. We create an empty box boundary like this. And then we need to create our particles. So now we skip this setup here. We do a loop here instead. We do for E and range, we do a 100 here. And then we need to create some variables here. So in this case, we can do random uniform. That is it returns a value between 0 and 600. And then we create our particles. And then we set also a random speed of the particle. And then we append the particles to the list. So we are going to use the that you can loop over and update them all at the same time. So we also need to update our drawing functions. So background here, we skipped that. Now we have to do a loop. So let's do self in p.particles. We need to update first. Then we have to check the boundary. And then we need to draw the particle. So let's see how it looks. So now you can see I have 100 objects of the type round particle. They all are updated in the same way. They share the same properties. But now you see they have the same colors here. So we need to do something about that as well. So let's do... We can also do p.stroke color equals, and then stroke alpha is like this. So now we vary all the colors here. So we vary the fill color. So every particle has its own color. So it knows, it has its unique values and attributes. So running this now, now you can see here, everything is, all these are of the type round object, of the class type round object. They all have their own colors, and we can all call them, draw them, just calling p.draw. And everything is handled like this. So I hope that this gave you a little bit more ideas on how you can use object-oriented programming and the benefits of it. So let's go to CALFEM. So CALFEM for Python, that is a toolkit that's been developed now, I think, more than 10 years at Structural Mechanics. So several years ago, we didn't use Python in this course. We used actually Fortran and Pascal. And the focus became too much on how to compile the code on the program. So we decided to go for Python. And we had a master thesis work that we looked at converting the Matlab version of CALFEM to Python. And now we have released multiple versions of the Python version. And we are like 95% of all the functionality of the Matlab version of CALFEM. It uses NumPy for matrices, so every time you have a matrix in CALFEM, it should be a NumPy matrix or an array. What we also have done with CALFEM for Python is integrate mesh generation routines. So we can use a mesh generator like GMSH or Triangle to generate the elements. So you don't have to manually do the topology and EDOF matrices. That can be done in CALFEM automatically. Plotting is done with Matplotlib, and the main modules of CALFEM is calfem.core. Those are the element routines and the system routines. So basically no graphical things in that. It's just base elements. CALFEM.utils, those mix of different functions, but there are some convenience functions for doing reading from I/O. There are some other useful routines that can be used. For the mesh generation, we have calfem.geometry. Contains classes for defining geometry of different kinds. So you can do splines, you can do lines and connect them together in a geometry, which is the base for generating the mesh. So then you have the CALFEM mesh module that actually takes the geometry and generates a finite element mesh. And it can also handle boundary conditions on the meshes as well, because when you're going from geometry, you will generate elements and nodes and degrees of freedom, and you need to be able to know what is a line in the mesh so that you can get the information of what degrees of freedoms are on a line, and that is part of the mesh routines. And then we have calfem.vis and calfem.vismpl. So we have actually two visualization libraries. One is going to be deprecated, and the one that we are going to use in this course is the VSMN20 library. And that contains routines for visualizing geometry, meshes, and results. You install, which you should have already done if you have installed a computer, pip install CALFEM Python. So I will do this in my notebook here as well. And CALFEM is not so much object-oriented. So CALFEM is basically a collection of routines for accomplishing, creating stiffness matrices and element matrices. The mesh generation is object-oriented. But you will see it is very easy to use as well. I think that is done, yes. Yeah, and now you probably, if you have done some finite element courses at structural mechanics, you will probably know the drill here. So you define the model, you generate the element matrices, you assemble the element matrix in the global stiffness matrix, you solve the system equations, and you calculate the element forces. And if you have seen CALFEM before, you probably know this super simple example with springs with different stiffnesses. We have 3 degrees of freedom, so you can't even get more simple than this. So first, we start by importing the things we need. We need NumPy, of course. We need calfem.core, and you can see here that I use a convention here that calfem.core stands for CFC, so CALFEM core. And then we have CALFEM vismpl CFV. So this is the convention I've created for CALFEM for Python, so it's easier to write the commands. Also to note that CALFEM uses the MATLAB degrees of freedom always start at 1. So we don't have 0 degrees of freedom, other than 0. So we have the same, if you look at an example in the CALFEM manual, the degrees of freedom are numbers from 1 to n. The same thing here. So if you define your degrees of freedom, you never have a 0 in that array. Internally, we will reduce, subtract 1 on all the topology to kind of make it work. But we wanted to have it the same experience as with the MATLAB version. So let's define the element. That's why I don't like using Notebook, because you can execute them in any order and you can forget to execute things as well. So it's problematic. So now this should work, yes. So now you can see I have a topology matrix here with 1 to 2, 2 to 3, and 2 to 3 here. Then we need to define a stiffness matrix, and I do np.zeros to create a 0 global matrix. and a 3x1 force vector. Looks like this. I create my element matrices. So this example is very like the manual. So there is no loops and nothing. We do every step manually. So I define the stiffness springs here, and I create the element matrices. And here you can see we have the same commands as in MATLAB, in the CALFEM for MATLAB. So spring 1E, that is the element matrix for a spring. And we create 2 of these. Looks like this. And then we assemble into the global stiffness matrix. And when you reference the EDOF matrix, you of course need to use it from 0 to the 0. It's only the degrees of freedom numbering that starts at 1. So in this case here, I just put it in here, and ASM knows about the numbering from 1 to something. So you don't have to think too much about the numbering itself. And now you can see here it assembles into K, KE. One thing to note here, in MATLAB CALFEM, we will return K, F when we do this, or K, in the ASM routine. In NumPy, or in the CALFEM version here, we don't do that. We add to the K matrix directly. So this K here is modified inside the call, and we don't have to return it back here. And you can see here also we get the stiffness matrix. We solve the system by using Solvec, also in CALFEM. Almost the same syntax here. We have a force here, and then you also have to think about here. Here we apply force at the second degree of freedom. But because F is a NumPy array, it starts at 0, so we have to move that back 1 step. And BC here is an array with degrees of freedom 1 and 3. So we give them a list of degrees of freedom that are prescribed, and we give the force vector, and then we solve it, we get the displacement and the reaction forces out here to the left. So very similar to what you do in MATLAB. Element forces, we need to first extract the element displacement arrays here, and that we can do with the CFC extract LDisp. And we give the EDOF here, and then the global displacements, and then we get the element displacement for each element. And then we can use spring1s here, which is the MATLAB command, or CALFEM command again, to extract the element forces here. So let's move up the complexity. We do some bars. Those examples here you can find them in the CALFEM manual as well. So I'm just doing them with the CALFEM for Python. So we define our topology again, element topology. Also, we don't use this in CALFEM for MATLAB. We have one column that is for numbering. We don't use that. So we just give the degrees of freedom. So 1, 2, 5, 6, those are degrees of freedoms here. Now we have a bit bigger global stiffness matrix. We define our material attributes and the section areas. Define our element properties like this. And then we do the element coordinates x and y. We call bar to e here instead of spring. We give all the parameters here, and then we get 3 element matrices back, and then we assemble them together. And then we solve the equation system here. Also note that when we do the boundary conditions here, in this case here we have boundary conditions that are 0. And then you only have to specify the degrees of freedom here, and by default it assumes that they are 0. If you want to prescribe a pre-described displacement, you need to specify a second array, like a BC values, that contains the prescribed values. And then you give that as a second parameters here, so BC values here, like this. I know this is not the same as in MATLAB version, because in MATLAB there is no distinction between integers and floating point, and we need to have these boundary conditions as integers for indexing and the values as floating points. So that we have in Python we have separated them into two distinct arrays. And you can see here the reaction forces here. And then we calculate element forces. So now we have done everything just manually, calling every function, assembling, and it's fine when you have 3 elements. But what if you have more? We need to have some kind of system to do this. So we have a bit bigger problem here. And in this case, we have 12 degrees of freedom, a little bit more elements here. We define our global stiffness matrix, our element coordinates. And now we start doing loops. And here, I told you some part when we do loops here that zip will be useful when we use CALFEM. So what we're going to do, we are going to loop over each element, each row in the EX array, and the EY array, and the EDOF array. And we extract those so that we get element X, element Y, and element topo. So these are slices of each of these arrays, and we use them as parameters to our stiffness matrix here, element matrix. And then we assemble this in here. So in this case, we don't do the manual. We have a automatic procedure for assembling our system. Then we apply our loads and our boundary conditions. And then we go the other way around. We extract all the element displacement. So if you extract LDs, the EDOF and A, you will get out an array of all the element displacements. And then we create an array for storing the forces in the bars. And we just create an empty zeros element here. And then we do the same thing but the other way around. So now we loop over EX, EY, and ED. So we have LX, LY, LD. And we use that as input to our bar 2S. Element X, element Y. Element properties are the same for every element. And then the displacement for each element. And we extract the scalar here for n here and store that in the n array. And we print it out like this. You can also mix different element types. And here we have defined, here we're going to use a bit different concept here. So we are going to define the coordinates of the system and the degrees of freedoms for each coordinate. So in this case, we have 2 types of elements. We have beam elements that has 3 degrees of freedoms for each node. And we have bars that only use 2 of them. So you can see here I have 1, 2, 3, 4, 5, 6, but the bars will only use 1, 2, 4, 5, 7, 8, etc. So let's run this. And then we have element properties here. Topology for our beams. You can see you have 1, 2, 3, so there are 6 degrees of freedom for each beam. We have EDOF 2 for our bars. And then we can use the chord extract function. That will take the EDOF, chord, and DOF and create element coordinates for each element. And we do that separate, so we have EX for the beams and EX for the bars. And then we have 2 loops. We assemble the beams first, very similar to how we assemble the bars. So we must do it in 2 steps because we have different element routines that we call. And then we do BC prescribed np.arrays and we solve back here. So next week I will go through the mesh generation. So in this next worksheet, you will work on creating a really simple structure using only it's 4 elements basically that you have to assemble together, and that will be a model for this worksheet. And then the next worksheet you will go through a geometric model instead, and then it will generate much more elements. But basically your solver should be able to handle small projects, small models, but also large models. So the thing you write as a solver will be able to take the input from the mesh generator into this as well. So I think this is what I wanted to talk to today. And then we have an exercise this afternoon as well. I'm working on. I've updated an installation instructions on the VSM reader docs page for Windows. I'm working on the Mac. I haven't had access to Mac, but now I have. So I'm working with that. So if you have problems, I hopefully I can help you more with that, and you can help yourself as well in that.